This is one motivation, this comparison to theory. The other motivation is find new exotic states of matter that no one has actually started to think about. No one has started to write down an equation that predicts that state of matter. Sometimes it's good to just be curious and go different ways and try to turn different knobs that you just haven't touched before, just to see whether there's maybe a new state of matter around the corner that will tell us something new about the world. That's the other motivation.
At the National Institute of Standards and Technology, or NIST, in Boulder, Colorado, scientists use laser cooling and trapping techniques to create ultra-precise clocks. David Wineland is the leader of the group that researches ever more precise ways to establish the basic unit of time, the second.
I would say in the business of clocks, it has always been true for the last 10 centuries at least, that when a better clock was built, a use was immediately found for it.
Continue 0.2 miles, then turn right on Lake Street.
For example, the global positioning system. In order to capture the information correctly, you need to know what time it is to nanoseconds or less precision. So you might ask, well, aren't we good enough now? I think the answer is no. And I think this is unending.
But beyond the advances in practical applications, more accurate clocks might even challenge our current understanding of one of the fundamental interactions between matter and energy.
On the more fundamental side, what we're always hoping for is that we might discover something that nobody has seen before. For us to be kind of hitting the jackpot. Of course, we aren't banking on this, but we certainly want to keep our eye out.
Time and frequency can be measured more accurately than any other physical quantity. Thus, ultra-accurate clocks can be used to test our physical understanding of the atoms that comprise the clocks themselves. Physicists have always assumed that the electromagnetic force binding the electrons to the nucleus of an atom is constant in time. But hints from astronomy and geology have recently brought that assumption into question.
There are theories like Einstein's theory of general relativity that simply don't allow the fundamental constants to change. There are theories that do allow the fundamental constants to change. Those that don't allow it will have to make adjustments if we do see some drift in the fundamental constant. So it's exciting.
Because atoms in the NIST clocks depend on the strength of the electromagnetic force, which physicists call alpha, the clocks will run slightly fast or slow if alpha changes. To test the controversial idea that alpha may be changing, NIST scientists look for slow drifts in frequency between two extremely precise atomic clocks in the laboratory. And what determines the precision of a clock is the precision and accuracy of its frequency standard.
A good example of a frequency standard is the classic one, say a pendulum oscillating back and forth in a grandfather clock. And there it oscillates back and forth maybe once a second. And at NIST, and basically that's the name of the game for us. We're just trying to make oscillators that oscillate back and forth at a very high and precise frequency, and one that doesn't change in time.
Atoms provide the answer. We know that when an atom absorbs a photon with exactly the right energy, an electron will jump to a higher level. A photon, a particle of light, can be thought of as an electromagnetic wave with a particular oscillation frequency. Different photons have different frequencies along the electromagnetic spectrum. A low-energy photon will have a lower frequency than a high-energy photon. The precise energy of that photon defines the frequency of the oscillation in an atomic clock.
So the nice thing about atoms for clocks is that the atoms, as far as we know, all atoms of a given species, they run at exactly the same frequency.
Cesium atoms run at a frequency of around 10 billion cycles per second, which corresponds to a microwave frequency. Researchers at NIST create very stable cesium clocks by trapping a cloud of cesium atoms and interrogating that cloud with microwave photons. They tune the photon frequency and watch how the atoms respond. The probability that the atoms will be excited out of their ground state reaches a peak when the photons are tuned to exactly the right frequency.
If the atom is oscillating at around 10 billion cycles per second, then we've divided up the second by finer and finer steps, and we get higher precision.
The cesium clock is precise enough to have served as the worldwide standard for the second for over 40 years. However, NIST senior scientist Jim Berquist and his team are doing even better to search for time variation in alpha.
Since all of us are scientists, it's not simply that we're making better time standards, better frequency standards. It's saying to us that we now have the tools, the wherewithal, to do some very interesting experiments in physics, test of fundamental laws.
This has prompted NIST scientists to develop clocks using much higher optical frequencies.
Advantage of going to the optical versus staying in the microwave region is that the information comes so much more quickly. A second now is defined as 10 billion cycles per second, roughly. That's a transition in the cesium atom. But if you go to the optical, you'll have 10 to the 15 tick marks in 1 second. And so the ability to make precision measurements in a short amount of time has jumped enormously.
Jim and his team have built one such clock. It uses one of the energy transitions of the mercury atom as its reference frequency, and is precise to more than 1 second in 1.5 billion years. The world's most precise frequency source. The mercury clock is one of a new generation of single-atom systems based on the frequency of a tightly confined ion, or a charged atom in a trap.
Normally in an atom, you have an equal number of electrons and protons, and so the atom is neutral. In ion, you have one or more of those electrons removed.
Removing the electron gives the ion an electrical charge, so it can be suspended in a trap by electric forces.
So that's how we trap it. Then, since it typically is hot, we laser cooling, whereby lasers are at the right frequency brought to bear on the atom.
Once the ion is cooled to the desired temperature, they bathe it with light at exactly the clock transition frequency. Having only one ion means that, unlike the cesium clock, they can precisely understand and control environmental factors that might otherwise cause frequency shifts. The result? Much precision.
We apply radiation at these roughly 1,000 trillion cycles per second. And when the radiation is tuned to a particular value, then it causes the energy state of the mercury ion to go from a lower energy state to a higher energy state. And that only occurs with maximum probability when this incoming radiation is tuned to the exact vibration frequency of this transition of the mercury ion. So we can clearly see this effect, and we see the atom blink on and off, and we know when it's either made the transition or it hasn't.
The exact frequency of the mercury ion clock is the most precisely known frequency in the world. But it depends on alpha, the strength of the electromagnetic force. If alpha grows, the energy levels of the mercury ion will move closer together and the clock frequency will be slightly lower. If alpha shrinks, the energy levels move further apart and the clock frequency increases. To check the stability of the mercury clock, the NIST researchers compare it to a clock based on a single aluminum ion that is almost as precise. The mercury clock frequency is 400 times more sensitive to changes in alpha than the aluminum clock. Therefore, if the team compares both clocks for a long period of time and alpha is changing, it will affect the mercury clock more, and they will see an unexpected drift between the two clock frequencies.
In our recent comparisons of two optical clocks in our labs here, we haven't seen anything yet.
So far, NIST has found that alpha is constant, at least to a few parts in 10 to the 17 per year. The drift in alpha, if it exists, must be smaller than that, and they can only detect it by running their experiment for a longer period of time.
If we saw something, first of all, we'd have to expect that, we just did something wrong. We didn't account for, say, a magnetic field in the right way. But if we could somehow rule out all the effects that we know about, we might be able to say something about that. Well, there's a new fundamental effect there. So this is, I think, any physicist's dream is to discover some new effect.
Whether or not they discover new and unexpected properties of nature, atomic physicists, including David Wineland and Jim Berquist at NIST and Martin Zweerlein at MIT, are using the techniques of trapping and cooling atoms, not just for their many potential practical applications, but in search for a better understanding of the quantum world.